Alignment Methods from Weak to Strong, OpenAI Super Alignment Team's first paper, How to Let AI Supervise AI. If humans cannot supervise superintelligent AI, can AI do it? Hello, folks, this is Skywalker X, welcome to my channel. In the past year, large models rooted in predicting the next token have dominated various tasks in the human world, showcasing the immense potential of artificial intelligence. Ilya Sutskever boldly predicts that if a model can effectively predict the next token, it implies an understanding of the profound reality that led to the generation of that token. This suggests that if AI continues to develop along its current path, a superhuman artificial intelligence system may emerge in the near future. However, a more worrisome aspect is that superintelligent AI may bring about unforeseen negative consequences. This is where alignment becomes crucial. The future AI systems may perform highly complex and creative actions, making it challenging for humans to supervise them reliably. Once AI surpasses human intelligence, how do we supervise AI systems much smarter than ourselves? Will human civilization eventually be disrupted or even destroyed? Even influential figures like Hinton express a pessimistic view, stating that he has never seen a case where something of higher intelligence is controlled by something of far lower intelligence. In July of this year, OpenAI announced the formation of the Super Alignment Team, with the goal of addressing alignment issues in superintelligent AI within 4 years. The objective is to understand how to build a trustworthy AI at the level of human intelligence and then use it to solve alignment problems. Recently, the team released its inaugural paper, claiming to pioneer a new research direction in empirically aligning models beyond human capabilities. In this paper, OpenAI draws a simple analogy to address the question of human-supervised superintelligent AI. The analogy involves using a small model to supervise a large model. Today, we will discuss this paper. In essence, the paper validates a simple intuition: using a weaker model to annotate data and refine a stronger baseline model produces better results than the weaker model alone. From this conclusion, it can be inferred that refining a strong baseline model with human-labeled data can surpass human performance. The paper aligns with OpenAI's style, seemingly stating a small rule, but when scaled up, it can yield miraculous effects, echoing the proverb inch by inch, it's a cinch, yard by yard, it's hard. The paper first suggests that research indicates a 1.5 billion parameter GPT-2 model can be used to inspire most capabilities of a GPT-4 model, reaching performance levels close to GPT 3.5. This indicates that powerful models possess implicit knowledge of how to perform tasks, even when given coarse instructions. We now know that AI companies primarily use human feedback reinforcement learning, RLHF, to train or align large language models, such as ChatGPT. Generally, this involves reinforcement evaluators assessing high-rated behaviors and penalizing low-rated ones. However, a challenge arises when supermodels produce complex and creative behaviors beyond human understanding. For example, a code generated by a super assistant model may comprise up to 1 million lines, making it impossible for humans to provide reliable supervision for key alignment tasks. These tasks include ensuring that the code follows the user's intent, the assistant model truthfully answers questions about the code, and the code execution is safe, among others. Therefore, if we fine-tune a supermodel under human supervision, it is highly likely that we cannot determine how the model will generalize to complex behaviors that even humans find challenging to supervise. In other words, even with human guidance, the performance of these supermodels remains uncertain when dealing with complex or unknown situations. This poses a challenge for aligning supermodels. How can less intelligent human supervisors control models much smarter than themselves? This is a weak to strong learning problem. Generally, traditional machine learning assumes that models supervised by humans are weaker than humans. However, for the ultimate superalignment problem, models supervised by humans are actually smarter than humans. Therefore, the team began researching a similar problem: how to use a weak model to supervise a strong model. To address this problem, the paper's team implemented the following approach for a given task. First, they fine-tuned a smaller pre-trained model on ground truth labels to construct a weakly supervised model, referred to as the baseline model, and the performance of this weak model is termed weak performance. Next, weak labels were generated through predictions of this weak model. Subsequently, a strong model, referred to as the strong student model, was fine-tuned using the weakly supervised model-generated weak labels. The performance of this model is termed weak to strong performance. Finally, the strong model was fine-tuned using ground truth labels to train a strong model with ground truth labels as an upper limit, and the final performance of this model is referred to as the strong ceiling. Generally, the performance from weak to strong falls between weak performance and strong ceiling performance. The paper defines the performance gap recovered, PGR, as a function of the three performances, weak, weak to strong, and strong ceiling. If perfect weak to strong generalization is achieved, the PGR is 1. If the weak to strong model's performance is not better than the weakly supervised model, then PGR is 0. The paper then presents experimental results in NLP tasks, chess, and reward modeling tasks, evaluating the performance of strong student models. Overall, in all weak to strong generalization experiments, it is observed that strong student models consistently outperform their weakly supervised models. For example, in NLP tasks, the results are promising, with the fine-tuned models performing better than the weak models, and the performance improving with the increase in the size of both weak and strong models. However, in chess and reward modeling tasks, the results are not as favorable, with the performance possibly not improving or even decreasing. The paper proposes several simple methods to significantly enhance weak to strong generalization. For the chess task, it is observed that when there is a significant computational gap between weak and strong models, the performance decreases. Therefore, the authors attempted bootstrapping by gradually fine-tuning a series of models from weak to strong, for example, using an intermediate model size for guided supervision. Although this significantly improved the performance in the chess task, it did not yield the same improvement in NLP or reward modeling tasks. The paper suggests that the poor generalization in reward modeling tasks is mainly due to the strong model fitting errors in weak model labels. As a remedy, an additional loss is added during fine-tuning, encouraging the model to maintain confidence when its predictions are inconsistent with the fine-tuning labels. This additional loss led to substantial improvement in the reward modeling task. Another method proposed is to enhance representation learning through additional unsupervised pre-training. After proposing these optimization methods for weak to strong generalization ability, the authors further analyzed two main issues in this setting. One is that stronger models tend to mimic the errors of weakly supervised models, which can be mitigated by adding extra loss or using early stop and regularization methods. The other issue is whether a strong model's ability to trigger certain capabilities depends on the baseline model. For instance, some tasks may perform well with simple prompt engineering, and whether a capability is triggered depends on whether the baseline model possesses that capability. If not, some methods, such as pre-fine-tuning a strong model on reward modeling data and then further fine-tuning for ranking, can offer improvements of 10 to 20%. While this paper represents a simulation, the ultimate ability to create models surpassing human performance is yet to be verified. However, the authors outlined several important directions in the end, including setting up simulated environments to avoid strong model fitting errors, addressing pre-training data leakage, and scaling methods. The ideal scenario is to find unsupervised methods as the current experiments rely on ground truth. Additionally, a more scientific understanding is required, as the paper provides experimental results but deeper comprehension of why these methods are effective and in what scenarios remains necessary. In OpenAI's plan announced in August, the core idea of superalignment is to train a model at the human level, then let this model train a model surpassing humans, continuing the alignment philosophy from before. Instead of using strong human data to train a weak model, this paper proposes the reverse, using weak human data to train a strong model. The question arises, at which moment does the model surpass human capabilities? From past experiences, the core logic is likely to be the same, with intelligence emerging most likely from the scaling of computational resources, involving the growth of data and model size. In OpenAI's August plan, the idea was to surpass humans during the alignment stage, first using an AI research assistant at the human level to autonomously plan the experimental process and provide supervision signals for training models, then scaling this process, while the AI research assistant itself is also a model, allowing it to iterate with new models until a computational threshold is reached, leading to surpassing humans. However, from the setting of this paper, it appears to be surpassing humans during the pre-training stage, aligning a strong baseline model with human data, even if the labels are not entirely correct, but still achieving performance beyond humans. The difference between whether to first have a stronger alignment model or a stronger baseline model for alignment is substantial. One is the work of the alignment team, and the other is the work of the pre-training team. Furthermore, if everything progresses smoothly, and a strong baseline model is trained, along with an alignment model surpassing humans, how can continuous iteration be achieved to become even better? How do we know if the model has truly surpassed human performance? By how much? The subsequent iterations need to ensure continuous improvement. The authors may also be considering these aspects, as evident in their attempt at weak-to-strong generalization in reward modeling tasks. If a strong baseline model trains a reward model that surpasses human performance, it can guide the alignment model to surpass humans. It also provides an indication of the model's general effectiveness. However, determining whether the trained reward model is over-optimized and how to evaluate the effectiveness of reward modeling is likely to be challenging. If anyone is interested in researching various alignment methods or solving related problems, OpenAI has announced providing funding of up to $10 million, encouraging exploration. Finally, alongside the publication of this paper, OpenAI has open-sourced the code for the weak-to-strong framework proposed in the paper on GitHub. It primarily includes an implementation of the weak-to-strong method for binary classification tasks, containing code for fine-tuning pre-trained weak language models and training strong student models using labels from another language model, serving as a reference for interested individuals.